Hello chemists, this is Ms. Placino and you are watching lesson 3.4 on element families. In today's lesson we're going to look at the similarities that elements within the same group exhibit. Now as a reminder, groups are the vertical columns on the periodic table. Sometimes they're called families of elements. So some goals for today's lesson. Explain why elements in the same group have similar properties. Be able to recall some general chemical and physical properties of the different groups. We're going to focus in on just a handful of them. Don't panic. You don't need to know ones for like all 18 groups of elements. And explain the observed reactivity of elements within a group. So lots of fun and interesting stuff to cover today. Let's get right into it. Okay, so I want to look at these four elements: lithium, sodium, potassium, and rubidium. Hopefully by now you're starting to get a feel of where different elements are in the periodic table, and you might know that these four elements are in group 1, the leftmost column of the periodic table. As you're taking a look at those electron configurations, what do they have in common? Yeah, they've got the same number of valence electrons. Lithium, sodium, potassium, and rubidium all have one valence electron, so one electron in their outermost shell. And it turns out that if you've got the same number of valence electrons, you're going to have pretty similar properties. So while the properties of these four elements won't be identical, they will be very, very similar. And this holds true for all the elements, all the families of elements, all the groups of elements in the periodic table. If you've got the same number of valence electrons, you can expect to see very similar chemical and physical properties. All right. So let's talk a little bit more about those group 1 metals. Do you know what they're called collectively? They're alkali metals. Alkali metals are not what you think of when you traditionally think of metals. They're extremely soft. You can actually cut them with a knife. They are shiny or lustrous, as most metals tend to be. Alkali metals react violently with air and water, and I've got a video to show you exactly what we mean when we say violently. We never find them as free elements. You'll never be walking down the street and find a rock made of sodium. They're way too reactive. Again, they react with air and water, so it is highly unlikely that you'll ever find them by themselves. They're always combined with another element or other elements as compounds. That's what we mean when we say never free elements. We just discussed this. Alkali metals have one valence electron, and really that's what leads to the extreme reactivity with air and water. You might be looking at this picture and it kind of looks like in this case, the alkali metal is under like some sort of liquid. Well, that definitely can't be water. Any thoughts on what that might be? If you're thinking something like an oil, that's a great guess. Yes, we keep alkali metals under oil as the oxygen in the atmosphere doesn't really tend to dissolve well in oil, and you have water and oil repelling each other, so hopefully that will protect the metal from any sort of interaction with air or water. These are hands down the most reactive metals on the periodic table. Doesn't get any more reactive from a metallic perspective than group 1 metals. Let's look a little bit more at their reactivity. So I've got a video to show you on how the alkali metals behave.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen, but this time corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a live flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Okay, that tends to be a video that really leaves an impression on people. If you go back to your notes, you've got a couple questions to answer about the reactivity of group 1 metals. The first one is explaining why group 1 metals are so reactive, and you're being asked to explain this in terms of electron configuration. Pause the video, get something down on paper, and turn it back on to check your work. All right, without question, group 1 metals are highly reactive. And it really comes down to the fact that they have just one single valence electron. They really want to get rid of that electron. A couple lessons ago, we talked about isoelectronic stability. By losing that one electron, they will have an electron configuration that matches a noble gas, which is extremely stable. So they will react pretty aggressively and violently to get rid of that one electron. The second question you're asked is to describe the reactivity as you go down the group. So from lithium to sodium, potassium, rubidium, and then cesium. And then try to explain why this occurs in terms of periodic trends. So same deal, pause the video, come up with an idea, turn it back on, and we'll review. Hopefully it's pretty clear to see that reactivity increases as you go down the group. You had just like a little bit of fizzing basically with lithium and water, and then with cesium and water, you saw the glove that the hand came in wearing. When that chunk of cesium was dropped off, you got like an explosion basically. So much energy and heat was released really quickly. So reactivity increases down a group. What periodic trend can we use to explain that reactivity? Hopefully you're thinking first ionization energy. We know that when metals react, they lose electrons, so they need to really become ionized. What happens to first ionization energy as you go from the top to the bottom of a group? Yeah, it decreases. It becomes easier and easier to take away that electron. So as less energy is required to remove the electron, that reaction can happen faster and release more energy. So the best way to explain the reactivity of the group 1 metals is through ionization energy. Since it requires less energy to ionize those large atoms at the bottom of the group, ones like rubidium and cesium, you end up with a much more violent reaction. All right, let's move one group to the right into the group 2 metals. Do you know what they're called? There are alkaline earth metals. They're also soft, shiny metals, not nearly as soft as the group 1 metals. They can be a little difficult to cut with a knife. They also react with air and water, but not as violently as our group 1 metals do. Due to their higher degree of reactivity, we rarely find them as free elements. They'll be bonded to something else in a compound, and we'd have to go through a chemical change to kind of split that compound apart back into its elements. The group 2 metals have 2 valence electrons, and that's why they're not quite as reactive as the group 1 metals. It is more difficult to lose 2 electrons than it is to lose 1, so they will not be as reactive as the alkali metals. We're going to tackle groups 3 through 12 all in one big swoop. Do you remember the name of that group? Yeah, those are the transition metals. They're nowhere near as reactive as group 1 or group 2, but when you think about metal, this is probably the type of element you are envisioning. They're very strong, shiny metals. You don't have much of a chance of cutting through these with a knife. The big thing to take away about the transition metals at this point in the game is that they form very brightly colored compounds. So when they react to form a compound, Lots of those compounds are soluble in water, and that's kind of what's happened here in this picture, and we get those really, really brightly colored compounds. It's due to the presence of transition metals, more specifically the d electrons in transition metals. And the number of valence electrons is going to vary from group to group, and really just different rules kind of govern how they're going to lose electrons that we see in the S and the P block, and for that reason we kind of gloss over them at this level of chemistry. All right, we're going to skip over groups 13, 14, 15, and 16. If you were to look at those on the periodic table, those are the groups where you start having kind of a mix of metals, nonmetals, and metalloids. So it's a little bit more difficult to kind of provide characteristic behaviors or properties of those groups of elements. So we're going to skip all the way, well, I guess not all the way, but pretty far to the right, group 17, fluorine, chlorine, bromine, and iodine, also known as the halogens. All of the halogens, kind of a fun fact, are diatomic. This looks like an empty tube. It's not. It's F2. It's just a gas. Chlorine kind of has that yellowish green color, Cl2. Bromine, one of our two liquid elements on the periodic table, it's very volatile, which means it's going to turn into a gas very, very readily. You don't have to increase the temperature much to get bromine to boil. And finally, we've got I2. If you're wondering about AT, it's pretty rare, so we often just kind of leave astatine out of the conversation. These elements react violently with all other elements. Kind of a fun fact, all three phases of matter exist at STP. Again, we've got fluorine and chlorine as gases, bromine as one of two liquids on the periodic table. Do you know the other? It's mercury. And iodine at room temperature is a solid. Also very volatile. It tends to sublime pretty readily to form a purplish gas. Our halogens as group 17 nonmetals have 7 valence electrons. Just like group 1 metals, they are dangerously close to completing their octet and will react in pretty dramatic fashions to get that to occur. These are the most reactive nonmetals on the entire periodic table. Now, I've got a video that I want to show you about their reactivity. And kind of given what we've talked about with metals and nonmetals up to this point in time, I want you to kind of make a bet with yourself about which one of these group 17 halogens is the most reactive. And we'll watch the video, we'll see how you did.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colourless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the coloured vapours, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2, and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction.
Just really quick, sorry to interrupt. One common misconception that students tend to have is that like fire is coming out of that hose. It's not. It is fluorine gas. Those F2 molecules are just coming out of there and they're reacting with the steel wool and the charcoal so aggressively and so violently that enough heat is liberated at once to basically make it set on fire. So we are not lighting those two chunks of solid on fire. We're hitting it with fluorine gas, and the reaction is producing fire.
With hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion.
And just
now
fluorine
you can
gas.
see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr, and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases.
They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride.
To make hydrochloric acid.
Now let's see how the halogens react with aluminium.
Aluminum.
When aluminium powder meets chlorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of the pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all four of these reactions are white solids, and they're all trihalides. AlO3, AlCl3, AlBr3, and AlI3. Now aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
All right, another group of really exciting and fun to watch reactions. Okay, so let's talk about the reactivity of the halogens. If you look back in your notes, you're asked to explain why the group 17 elements are so reactive in terms of electron configuration. Pause the video, come up with an idea, turn it back on to check. Well, in terms of electrons, we know that all elements are striving to complete their octet. Halogens have 7 valence electrons. All they need to do is pick up one more electron, and they have a complete octet, which we know makes them very, very stable. So since they're so close to completing their octet, they're going to react violently when they're able to complete it. So it's really the fact that they are so close to having a complete octet that will drive their reactivity. The second question asks you what happens to reactivity as you go down the group. And I think this is usually a little bit harder for students to deduce than with the alkali metals. Think about the reaction with aluminum and how quickly it occurred, and if anything had to be added, like heat, in order to push that reaction to occur. As you go down the group, reactivity decreases. Fluorine is the most reactive elements in group 17. When the aluminum was added, it reacted immediately and at room temperature. With the chlorine and the iodine, I believe, you had to heat it up in order to get that reaction to occur. And there was a delay with bromine reacting with the aluminum. So the fluorine reaction is the fastest, and that's going to release the most energy. Now, trying to think about this in terms of periodic trends is, again, a little bit more difficult. A lot of students want to point at the electronegativity trend, the ability to attract electrons in a bond. And that is not a bad guess based on what we've learned about. But electronegativity is not driving reactivity here. Well, it probably isn't first ionization energy either, because you've got first ionization energy is about removing an electron, and we know that that is not the case with the halogens or nonmetals in general. They tend to gain electrons. And atomic radius just talks about atomic size, not really gaining or losing electrons. I guess this is a bit of a trick question based on what we've talked about so far. And there's another trend that will come up in AP chemistry called electron affinity. And what electron affinity is, it's the amount of energy either released or absorbed when an atom gains an electron. When the halogens gain electrons, they release energy. So fluorine, when it becomes the fluoride ion by gaining an electron, releases a ton of energy. Chlorine, bromine, and iodine fall into that same category, just not quite as much energy as fluorine would release. So again, a little bit of a trick question. I won't bug you with that explanation on anything like a quiz or a test, but it's really driven by electron affinity. So just to help you get a definition down, electron affinity is the amount of energy released or gained when an atom gains an electron. Halogens always release energy when they gain an electron, which is why we see that reactivity down the group. All right, let's finish up our groups. Group 18, by now you probably know them as the noble gases. All of them are gases, as the name suggests. Under normal circumstances, they're not going to react. Helium, neon, argon are like completely inert. Try as you might, you can't get them to react. Krypton and xenon will react with something like fluorine if you really force them to. But generally speaking, do not react. Again, we call that inert. It does not react. We know that they don't react because they already have a complete valence shell. They've got 8 electrons in their outermost electron shell, and that leads to stability. There is nothing to gain for the noble gases by reacting with other elements. These are the least active reactive elements on the entire periodic table. Nothing is going to come close to their inactivity. All right, so that really wraps it up. You should know the alkali metals, group 1, alkaline earth metals, group 2. Know that groups 3 through 12 are transition metals and are really known for being colorful. Group 17 are halogens, group 18, noble gases. Those are the ones that I'm really going to hold you responsible for. Now, given what we've learned about, what 2 elements would you really like to see react? We know that all of the main group elements, and again, when we say main group elements, we're talking about the S and P blocks, groups 1, 2, 13 through 18. All these elements are trying to achieve an octet of electrons because that is going to be a really stable configuration. And we know that reactions are going to occur so that elements can complete or fill their valence shell, whether that's gaining or losing electrons. So, what do you think is going to happen if we take one of the most active metals and combines it with one of the most reactive nonmetals? Yeah, that's the type of reaction that people like to watch. So, which 2 would you probably select? Most students point at like either francium or cesium. Again, francium is extremely rare, so it's unlikely you'd have any of that to react. So we'll go cesium and fluorine. We've got the most active nonmetal reacting with the most active reactive commonly found metal. We know that we've got group 1 metals just trying to lose an electron, group 17 nonmetals trying to gain an electron. It's kind of a match made in heaven. And you've got those really large atoms on the metallic side of the periodic table with low ionization energies. And then you've got the small atoms on the nonmetallic side with electron affinities that will allow them to release a ton of energy when they pick up that electron. So, unfortunately, try as I might on the internet, I cannot find a reaction between cesium and fluorine, but I can find one between sodium and chlorine. So let's go ahead and watch that.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
That reaction happens really, really quickly. You've got a very small chunk of sodium metal, something that if you put it in water, it tends to explode. And then it's surrounded by chlorine gas, a gas that was used as a chemical weapon during World War I. It is extremely irritating to your lungs. It's kind of crazy that when you combine these two, you come up with sodium chloride, something fairly innocuous. This reaction occurs as quickly as it does and releases so much energy because you've got really that perfect pairing, an alkali metal with one valence electron that it is desperate to lose, and a halogen that is just one electron short from completing its octet. So when that matches up, we are going to get some very violent reactions that happen quickly and release a lot of energy. All right, chemists, that wraps it up for today. Thank you so much for tuning in, and I hope you found this helpful.